All right, this is review video 36, thermal equilibrium and calorimetry. So to start off, we'll define thermal equilibrium, and it's a state at which two or more objects have no net heat exchange between them. But I want you to pay attention specifically to this word net, because it doesn't mean that heat isn't being transferred between the two objects at all. It means there's no net transfer, which means there's no net movement of heat from one to the other in like a singular direction. Couple of things with thermal equilibrium. For two objects to reach it, they have to be in physical contact with one another. Like, we can't have an object in one room and then an object in a completely different room reaching thermal equilibrium. That's not a thing. And those objects, when they reach thermal equilibrium, they will end up at the same temperature. So let's look at this little graphic to help us understand what's going on with thermal equilibrium. So over here at this side, we have two separate blocks. One is hot, that has a lot of energy. One is cold, does not have a lot of energy. The molecules within the hot block are moving a lot, right? They're vibrating a lot because this block is a solid block. So they're vibrating in place, but they're vibrating quite a bit because they have a lot of energy. The atoms in the cooler block are still moving a little bit. They're still vibrating, just not nearly as much. But if we make those two blocks touch each other, what we see is a net movement of energy from the hot block towards the cool block. And why that happens is the physical molecules that are touching each other between the blocks, we're transferring energy. That vibrational energy of the molecules that are touching each other are going to transfer in this direction. When those blocks reach thermal equilibrium and they are the same temperature, that means that all of these molecules on average are vibrating the same amount. That does not mean every single molecule is vibrating exactly the same. It means on average, we're seeing the same in each block. However, there's still going to be energy transfer between every single molecule that touches each other, right? Or is close to one another. But we're no longer seeing a net movement this way. Instead, we're seeing a lot of little movement from molecule to molecule to molecule. So again, energy is still moving, but we no longer see a unidirectional net movement anymore. Okay? So for two objects to reach thermodynamic equilibrium, again, we know that they're going to end up at the same temperature. So what controls what that final temp is? Because it's very rare for it to be a perfect average of the two original temperatures. Because like typically you would think, okay, great. So this block, let's say that was at 100 degrees and that block was at 0 degrees. So theoretically, we should end up at 50 degrees for that perfect average. But again, it's very rare that we end up at a perfect average. And the reason for that is because it's not just the original temperatures that control what the final temp is. It's also the mass of the object. So if the mass isn't the same, that can affect your final temperature. And also something called the specific heat capacity of those objects. So specific heat capacity, I'll explain further in a second, but essentially it's an object's ability to retain heat. And different substances have various abilities to do this. Like water is really good at retaining heat, but metals are not really good at retaining heat at all. So that ability of different substances can control what the final temp of our objects are. So if we imagine here we have a beaker of cool water. Let's say we put hot metal in it, but we only put a little bit of hot metal. Great. The thermodynamic equilibrium temperature is going to be closer to what the water was because there's way more water than there is hot metal. But let's say we put a really big block of hot metal in there, then the final temperature is going to be a lot closer to the metal than it is to the water. So again, that's how mass can affect it. But also we have to think about, great, well, can the water retain a lot of heat? Or can the metal retain a lot of heat? Like that specific heat capacity plays a role as well. So let's define specific heat capacity using science words. It is the amount of energy that it takes to raise 1 gram of a substance, either 1 Kelvin or 1 degree Celsius. And again, you can use either unit. The units for specific heat capacity are either joules per gram times Kelvin or joules per gram times degrees Celsius, and which unit you use depends on what you're measuring the temperature in. We use the letter C to represent specific heat capacity in formulas like Q equals mc delta T. There is one C value, one specific heat capacity that you should know by heart, and that is 4.184 joules per gram Kelvin, and that is specifically the specific heat of water. Why do you need to know it? Because it pops up all over the place. When we do calorimetry, 9 times out of 10, water is going to be involved somehow, and you're going to use this number. On the AP test, sometimes they'll give you that value, sometimes they will not, and so it is very helpful to know the specific heat capacity of water. In terms of different substances, conductive substances like metals tend to have low specific heat capacities because, again, metals conduct heat, they conduct electricity, so they're not good at holding on to heat. But non-conductors or non-metals like water tend to have much higher specific heat values because non-metals do not conduct heat, so they're really good at holding on to it. Terminology that you could see, heat capacity versus specific heat capacity. So we already know that specific heat capacity is the amount of energy it takes to raise 1 gram of a substance 1 degree, and that could either be Celsius or Kelvin. Heat capacity is similar, but it's not the same. So a heat capacity is the amount of energy it takes to raise a substance by 1 degree Celsius or 1 Kelvin, but not specifically 1 gram of it, which makes heat capacity and specific heat capacity very slightly different from one another because heat capacity is going to vary by mass. So the higher the mass of your substance, the higher its heat capacity because it's going to take more energy to shift its temperature. So if we look at this, let's say an ice cube versus an entire bathtub full of water. It's water either way, but it's going to take much less energy to shift the ice cube in temperature because you're not talking about a lot of water with a little ice cube. Versus a bathtub, if you wanted to heat a bathtub full of water, you would have to use a lot more energy to do that because there's more water present. So again, if you have more mass or more of that substance, it's going to have a higher heat capacity. All right, so we understand all that now. Let's talk about Q equals mc delta T. This formula is what we're going to be using next week. It's the formula we use for calorimetry, and it has a few different parts. Q is energy in joules, specifically joules, not kilojoules. So if you get an energy value in kilojoules, you'll have to convert it. M is mass in grams, specifically. C is our specific heat capacity, and again, that can be in joules per grams Kelvin or joules per grams degrees Celsius. And then delta T is going to be our change in temperature, either in degrees Celsius or in Kelvin, and which one that shows up in is going to control what unit you use for your specific heat capacity. Sometimes you're not given a change in temperature directly. Most of the time, you're not given a change directly. And so to calculate delta T, you're going to take your final temperature and subtract your initial temperature, and that is going to give you delta T. All right, so let's deal with a practice problem. The practice problem says when 5.05 grams of a substance is cooled to 50 Kelvin and allowed to heat back up to room temperature, 298 Kelvin, it absorbs 1.052 kilojoules of heat. What is the specific heat capacity of that substance? All right, so we're going to use Q equals mc delta T because we have enough information to do that. 5.05 grams is going to be our mass because grams is the mass unit. That amount of substance is cooled to 50 Kelvin and allowed to heat back up to room temperature. So what we have here is we have an initial temp and we have a final temp. So to get delta T, all we're going to do is subtract the two. And so if I just do that really quick up here, I get 298 minus 50, and that's going to give me 248 is my delta T. When that happens, it's going to absorb 1.052 kilojoules of heat. If I look back up here, I know that that's heat, but it needs to be in joules, so I have to convert it. Every kilojoule is 1,000 joules, so this is 1052 joules. I'm asked for the specific heat of the specific heat capacity of the substance, so that's C. I don't know what it is. That is what I am solving for. So at this point, all I have to do is plug and chug. So my 1052 joules is equal to my mass 5.05 times my unknown C value times my delta T of 248 Kelvin. That's in grams. All right, now all I have to do is solve for C. But before I do that, I'm going to go ahead and combine like terms so it's a little bit friendlier to look at. 1052 joules is equal to, we're going to multiply those two together, and that gives me 1252.4 times my unknown C. I'm going to divide both sides by 1252.4. Goes away on this side. And we've got a C value of 0.840. Again, we have to stick a unit on that. My temperature was in Kelvin, and so it's going to be joules per gram Kelvin for my unit. Now with this value, this problem didn't ask me directly to do anything else, but sometimes you might have to identify a substance using its C value, and typically you'll be given a table off to the side to match this to. Sometimes it'll match the table exactly, sometimes it'll just be really close and you'll have to pick the closest option, but either way, this plug and chug formula should not be new for you. If you took baby chem, you would have used this already, so this should be pretty easy for you to do. If you have questions about it, please feel free to ask.